Uh, so I just need to finish a quick thing about the cross product to give you like the formula. In case you haven't seen like the announcements today, so you should have access on the Canvas site to Gradescope. And I posted, I posted two things. First, like this GeoGebra assignment, which is not due until much later, so you don't have to really worry about it. But if you want to kind of skim through it, like just to get like a sense of what's being asked, it's very straightforward because it's just basically, oh, go to GeoGebra, I give you the link for the application on GeoGebra, and just like take some screenshots of what you see there. So it's more for you to just kind of play along with some of the animations that I have been showing you. But again, that one is due like a few days before the exam, so it's not one to worry about for now. But you can still read it just if you're curious about like some of the animations because they are like kind of like useful to have around. And then the other one, which is due this Friday, is kind of like I think like 8 true false questions. So it should not take too much time because they're just like properties of the dot and cross product. So you can read through it, but I think most of them we kind of have already covered in one way or the other. If not, you can ask me on Wednesday if you like before class or after class. You can also ask during office hours. But I mean, they should be like relatively straightforward, like true false questions. But I do want probably for the exam, I do want to have just like a problem with just like a list of true false questions. So like the types of true false questions that we'll have on the exam are along the lines that you'll be seeing on the Gradescope side. So like you can call them more conceptual, but it's like I just like to think about them as like just like less computational. So it's not like a like that way you can ask a few more things without like any of them like requiring like too much time because it's either you know the property or you don't know the property kind of thing. So yeah, so do keep an eye on those because I will probably either post a few of them like exactly the same or just like small modifications in the ones you'll be seeing on the Gradescope assignments. So the thing that I was going to finish telling you about the cross product. This is already recording. Yeah. So if you remember last time, the cross product is between two vectors. And the idea is that it will give you a vector that's perpendicular to both of them. That will be very useful. Um, maybe today or next time when we talk about planes, for example. And the direction is found using the right-hand rule. So I won't go into that again, but the other important property of the cross product is the length of the cross product is just the product of the lengths and the sine of the angle between the vectors. Okay. So that's like kind of like the geometric way to think about the cross product, but it's also convenient to think about like a more like algebraic way to do it. And for that, that's why I has started telling you a little bit about the determinant last time, just because the determinant is like a very convenient way to memorize the formula. So just a reminder of what the determinant for a 2x2 matrix was. And if you take something like linear algebra, you'll talk a lot about the determinant, so it's not really something I want to focus too much in this class, except to give you what like the absolute minimum of things that you need to know. So like the determinant is just that you multiply the element along the diagonals and subtract the answer. Okay, so the determinant of A, it was AD minus BC. And again, this number actually has a lot of interesting properties, but we don't need them for this course. And then the other formula for that we need, like in terms of matrices, is for a 3x3 matrix. Okay, so besides the 2x2 case, we need also the determinant of a 3x3 matrix. So that is what I'm about to explain to you. And again, I don't really plan on like getting into the specifics of why it works this way. Like you should just really think about it, at least for our purposes, as a convenient way to memorize the formula. I'll give you in a few minutes about the cross product. So what is a 3 by 3 matrix? Like as you might guess, it's just like an array with 3 rows, 3 columns. So you just are, it's kind of like a nice convenient way of organizing 9 numbers. Okay, so you could call the entries that A, B, C, D, E, E, F, G, H, I. There are more useful ways of labeling the entries, but this is kind of what we need for now. And the determinant is going to be a number. So this is again going to be a number. But the question is what number, right? So here's how I'm going to tell you how to do it. So if you have the 3 by 3 matrix, just imagine that, actually, I'll draw it. Well, let me just draw it there, actually. So in fact, when you have a 3 by 3 matrix, you can create like a matrix of signs if you like. Let me call it like this. What do I mean by that? It just means that you'll have a matrix of plus or minuses. So I'll put a plus here, and the idea is that it always starts with the plus on the top left corner, and then it just alternate between plus and minus. So plus, minus, plus, plus, minus, plus, minus, plus, minus, and then plus, minus, plus. Okay, so it's like an alternating matrix of signs of plus or minus, and it always starts with the plus on the top left. And so the idea to find the way in which the determinant can be computed, again, whatever this is that you choose the first row. Okay, so, and again, in practice, there are other ways to do it, but this will be the way we'll do it for like memorizing the formula. So you'll choose the first row, and then you look at the first row and the table is matrix of signs. Okay. So what are you going to do? You're going to multiply each of these numbers by their corresponding corresponding sign as they appeared here. So let me put it like this. This was plus minus plus. So I'll put plus minus plus. Okay. So plus A minus B plus C. Okay. And then I'm leaving some space behind between the numbers because I'm going to do something else as well. Let me actually see if I can put this a little bit further forward. Okay, I think that should be fine. And then what do you do? So let's start with the first entry, which was A. So if you look at A, it belongs to the first row, first column of this matrix. So what you do is delete that. Okay. If you delete like the first row, first column of the matrix, you get like a 2 by 2 array. You get another matrix. So, but we know how to find the determinant of this. So essentially what you'll do is multiply this number by the determinant of this 2 by 2 thing that you get by removing the row and the column. Okay, so let me just write plus 8 times the determinant of EF HI. Okay. And then let's move to the next one, which is B. Okay, so if you look at B, belongs to first row, second column. So if you remove those, you get E, F, G, I, and so you take the determinant of that 2 by 2 matrix or array. E, F, G, I. Okay, and the last one, if you move to C, C belongs to first row, third column, right? So you remove first row, third column, and then you get this 2 by 2 matrix, right? And you see the determinant of that. So that is the formula for the determinant that will use, and I'm about to do an example to make it more concrete. It's completely weird, like completely unjustified the way I'm telling you how to do it, but the point that I'm trying to make is that to find the determinant of a 3x3 matrix, you actually compute a bunch of 2x2 determinants and then you just combine them in a funny way. Okay, that's one way to think about it. And then like the idea, which again we wouldn't need, is that to find a determinant of a 4x4 matrix, you compute the determinant of a bunch of 3x3 matrices and then compute them combine them in a funny way like that, and so on. So this is kind of like sometimes like if you do programming, like it's what you call like a recursive definition, because to find the determinant of a 3x3 thing, you need to know first what's the determinant of a 2x2 thing. And to find the determinant of a 5x5 matrix, you need the one of a 4x4 matrix, and then the one of a third 3x3 matrix, and then the one of a 2x2 matrix. So it kind of always refers to its ancestors. Like, to know the definition for like a larger matrix, you need all the previous definitions, but they kind of all build with the same structure. So that's kind of the idea. So let me do an example. Is there any questions first? Yeah.
I guess when finding cross products, if higher dimensions than three, you would need more than two vectors. right?
Oh, so well, I guess I should have said this at some point last time. So there's actually not a cross product for vector say with 4 or 5 entries. 3 is like the most that you go to. If you want to have like an idea of why that works, it's like and this takes a little bit of time to visualize. The thing is like if you are the cross product, you need to find a vector that's perpendicular. For the direction, we need a vector that's perpendicular to the two vectors you started with, right? In 3 dimensions, that's not too bad because there are only like 2 reasonable choices, right? Except for the size. That's what gets decided with the right-hand rule, like which of the 2 you pick. But say if you have 2 vectors in 4 dimensions, there's actually not just 2 choices. There's actually like infinitely many choices to choose from, because now they're like it's kind of like a circle's worth of vectors that are perpendicular to both of them. So there's really not like a good way to make a consistent choice of which vector to choose that's perpendicular to the 2 of them. So yeah, it does take a little bit of imagination, but my point is that actually there's something special about 3 vectors of size 2 or 3, because there like you can actually define the cross product. Cross product is not defined elsewhere. What you can do, again, which we won't get into this, like there's something called like exterior, like by vectors or exterior algebra, and then you can do something like that works in any size, but not like a cross product. So, but yeah, it does take a little bit of imagination, because like you have to think about things with higher dimensions. But unfortunately, there's no cross product, but there's like a modification of that construction that doesn't work. But cross product is special to 3 dimensions, basically. But no, I'm glad you brought it up, because I always feel like I should say it at some point. Any other questions? Yeah.
Why is B negative?
Okay, so there's no why here because I didn't give any explanations, right? So it's just like, at least for how I said the formula was like, each coefficient gets multiplied by its corresponding sign, and it just happens to be that, they alternate. Why do they alternate? I mean, this is like a black box, right? I'm not because those, like, that does take into a detour, like requires a lot more time. But yeah, so it's completely, not super clear, but at least there's like a little bit of an explanation for why this makes some sense. Because if you think about the 2x2 case, right? If you think about 2x2 case, what would be the matrix of signs here? It would be plus, minus, minus, plus, right? So if you chose the first row, right, you get plus A, right? Let me see if I can put like the same analogy here. You would do plus minus, right? So you get plus A minus B, right? And then if you follow kind of like the same recipe that I just gave you, you would see that what you are supposed to do here is kind of like delete the first row and first column, and then you just get a number. So there's nothing really to think too much about. You should just multiply A by that number. So you get plus AD. And then if you move to the first row, second column, you delete that, and then you just get another number, and then you get minus BC. So you see that if you, for some reason, if you had set it up things like this, then it does reproduce the formula for the determinant of a 2x2 matrix. So at least that kind of tells you what it had to be alternated for it to give you the correct result in the 2x2 case. And then like the point is like all the other ones are kind of built by analogy to this one, and that's what I meant, like kind of like, you know, building like higher structure from like copies of the previous one. So is that making that makes more sense? But again, it's kind of yeah, it is a long topic of how it's done, but at least hopefully this gives you like a better hit of why it cannot just be like all pluses, for example, because you did want these to coincide in the 2x2 case with what we knew. So that's kind of the idea. I'll kind of erase that in a second. Let me just do an example, and then I'll give you the formula for the cross product before moving to a different topic. So for example, if I had chosen A to be like 2, 1, minus 1, 1, 2, 3, 1, 3, -2. Okay, if I had said the matrix is this, what is the determinant of this matrix? So again, for us, we always choose the first row. Okay, so if you choose the first row, what happens here? You don't really have to do like all the matrix of signs. If you would like, you can just copy the signs that you care about on top of the row, right? So you can just put plus, minus, plus. So if you do that, you will do plus, plus, minus, plus. So it's plus 2, minus 1, well, plus, minus 1, right? It's fine. And then I just need a bunch of determinants. Okay, so again, what do you put there? So you get 2, 3, 3, -2. Then when you delete like the one that 1 belongs to, you get 1, 3, 1, -2. And then for the last one, for -1, you get 1, 2, 1, 3. And if you understand this part, then really everything else is just like a bunch of multiplications, right? So is it okay? How am I finding the matrices? Like that's really the most important formula. Like the most important part of this formula is just like writing the first step, because everything else is a little bit like just mechanical. So you just get 2. What is the determinant? This gives you -4, -9. Okay, minus what? So this is -2, -3. Okay, and then there's some a minus from this formula. So you get, I mean, there's a, because it's plus minus, it just gives you -1. So then gives you 3 -4, right? So let's just check. Because there are a bunch of multiplications, so it is easy just to make a silly typo somewhere, because you do have to do a lot of products. So you can, I think this looks fine. Okay, and then okay, so this gives you -13 with the 2, you get -26, and then this gives you -5 with the minus here, you get +5, and then this one gives you -1 with the minus, gives you +1. Oh, okay. This one that wasn't done on purpose, but it gives you -20, so that's not such a bad number. Okay, yeah.
I think for the last divide-two matrix,
Oh.
with 1, 2, 2.
Oh, yeah. So it should have been a 1 here, you're saying.
Oh, yeah, one there and then, oh, wait, yeah. Sorry.
You only have 1, right?
Yeah, that's the only.
Okay, cool, thanks. Yes, this is what I was referring to. So, okay, that's not too bad. Thanks. But yeah. because I have to delete this one, right? So 1, 2, 1, 3, yes, now it's fine. So 3 minus 2. Good, thanks. And then, okay. Not such a big difference, but it gives you -1 here instead of +1. And so what? Now it's a -21, right? Okay, so you see how.
It should have been.
Oh, -22, right? Okay, what am I doing now? So, yeah, no, -22, that's what you were saying. Okay, so none of the arithmetic steps are difficult, but you are doing so many of them that, yes, that does multiply the risk of like just making like silly mistakes, so. Like in fact, like in computer science, like you can ask like, okay, if you look at this formula, how many multiplications are required to do it? So like there's like a sense like, if like you have a matrix of size n by n, it's in like n squared or n cubed operations. Like, like you have to have like how big is the number of operations that you're doing, because like in the algorithms, like you do want like efficient that you could try to find like more efficient ways to find to compute this so that your time to compute like the determinant is reduced. When it's 3 by 3, this doesn't really matter too much because everyone can compute it in a reasonable amount of times. But it's like if it's like a 30,000 times 30,000 matrix, right? That can be like it could, like depending on your computer power, that can finding better algorithms like could save you time and money, resources, and other things like that. Okay, but yeah, so it is a good fact that think that like I made a couple of mistakes because you do have to be a little bit careful when you write, like double check every step, just because it is easy to like when you're rushing it, like to just like make a typo. But again, so it just gives you a number. I'm not kind of like going into detail of what this number means or whatever. Like it's just like we just get this number, okay? The only reason why I did this first is because again, like the formula for the cross product is easy to memorize with the help of the determinant. And so that's what I'm about to explain next for you. Is that okay? Any other question? So let me give you the formula for the determinant, for the cross product in terms of the determinant. And again, you actually can check it if someone is interested just by like writing everything in terms of IJK, foiling it, and just you check that it matches what I'm about to write. But it's again, not like not worth doing here, but there is a way. I mean, it can be verified if you just expand the vectors in terms of IJ and K and use a distributive property of the cross product. So it can be checked. You do have like the ability to check it. That's what I mean. So here's like a formula for the cross product. The idea is that if you have two vectors, let me call them U and V as always. So U is here, maybe. I'll write it as U1, U2, U3. And then V somewhere else. Just not trying to make my life complicated. So let me put V somewhere in here. So this V1, V2, V3. So what's the formula for the cross product? So the idea is that U cross V can be computed as a determinant. Okay. So again, it's kind of, think about it more as like a memorization trick, but it's kind of a nice one. So what's going to happen here? So here you have 1, 2, 3, 4, 5, 6 numbers, right? So definitely you cannot use like a 2 by 2 matrix because you already have 6. So the next option would be to do like a 3 by 3 matrix, right? That requires 9 things, right? So I'll just, you end up doing is like you take these first entries of the first vector and put them in the second row. And then you take the entries of the second vector and put them in the third row, and then you're still left out with three entries to fill in. And what you do is kind of like a little bit of a cheat because you're going to fill it in not with numbers, but with vectors. So the vectors you fill that in with are the unit vectors. So I'll put ijk. I'll put ijk there. And again, what does that mean? If you, so I'm giving you the way to memorize this. So what does that mean? What is this actually equal to? Well, if you look, if you do the expansion of the along the first row, that is plus I minus j. So let me put it like this: plus I minus j plus k, right? And each of these like gets multiplied by a determinant, right? So I'll just write down the entries that you have to put there. So, when you delete the first entry, you get these 2 by 2 matrix. So the determinant will give you U2 V3 minus U3 V2. Okay. When you delete the J spot, you get U1 V3 minus U3 V1. Okay. And then when you do the last entry, you get U1 V2 minus U2 V1. Okay, so this is going to be a vector because it's a number with the times I plus times like, or minus a number times j plus a number times k. So it's in terms of ijk. So anything in terms of ijk, it is going to be a vector. It's just that, if I had just written this last step, which is like the actual formula, there's not like a super obvious way to memorize it. But if you set it up in the matrix version first, then it is easy to memorize, even though it's kind of like weird, the setup looks a little bit odd, but it's just that one is faster, like to execute, let's say. So I'm about to do an example. So like you just see how the vectors come out at the end of the beginning. And again, if you actually wanted to verify this, like what you can do is like expand the vectors in terms of ijk, and they use like the foiling property or like distributive property of a cross product, and then you just play a little bit with the formula, and you will get this one. I'm sure I have done it. I mean, I did do it like I did it last time for the case when the last entries were 0, so it's kind of like an extension of that idea. But it's just that it's a little bit tedious, to be honest. And so that's why I'm trying to skip that. So let me give you an example. Just make things more concrete. Oh, by the way, implicit in the list, it tells you that the order it kind of shows you in some indirect way that the order doesn't matter, in the sense that, this one goes into the second row and the other one goes into the third row. So like the positions in which they appear on this matrix does depend on how you wrote it. So there are properties of the determinant that essentially it tells you if you swap 2 rows, then the determinant gets multiplied by a -1, and that's why that's related to, swapping the factor here, like the order in which they appear gives you like a minus in the formula, V cross V is minus V cross U. So imagine, like, let's say vector U is this, vector V is like 1, 1, -1, again, just to do simple numbers, like I'll put a 2 here, actually. I'll do simple numbers because that's enough to show you what's happening. So you determine what is the cross product using this formula. So you set it up as a determinant. Put ijk on the first row. Then the entries of u in the second row, so 1, -2, 3. And the entries of v in the last row, so 2, 1, -1. Okay. And again, there's going to be, so it's plus minus plus. That's like the first thing you should write probably every single time. So plus I, which no one really writes, but you know, when it's plus, like you don't have to write the plus, but I'm just putting it now for emphasis. Okay. And I'll write the determinants explicitly just to help you out and also myself, because I don't want to be doing like all those multiplications in my head. So when you delete this row and column, you get 2, -3, 1, -1. Okay, when you delete j, you get 1, 3, 2, -1. And then the last one, when you delete the k1, you get 1, -2, 2, 1. So let's check. I think it looks good, but if someone notices any issues, let me know. So we're almost done. Just have to finish doing this determinant. So you get I times like, so this gives you 2 -3 minus j. This one gives you -1 minus 6 plus k, which gives you 1, right? And then there's a minus from the formula. So this would have been -4, but there's a minus from the determinant formula, so it becomes +4. Okay. And we're almost there. So this just gives you -1. So it is like this -1 makes more sense to put it in front of the I. So you put -I, and same was with the other ones. Like, so this one gives you -7, but there's a minus here already. So that becomes +7j. And this one gives you 5, and again, it makes more sense to move it like to the front. So you put +5k. Okay, so it's like, you know, like notation wise, it looks better to have like the numbers before the ijk's. Is that okay? And now this looks like more normal, you know, it does look like a vector, you know. So it was always a vector because again, it was like numbers times ij and k. So the difference is that with ordinary, like, you know, if you had been like an ordinary 3x3 matrix, you know, you can't go, you would have finished combining these things. But the thing is, like, now since you put like vectors in the first row, you know, there's no other way, like, you know, to combine them, like this actually, the only way to combine them is to rewrite this as -1, 7, 5. You know, if you prefer to write it in another way, but the thing is like these are not numbers, so you cannot, you know, you're not going to get a number as the answer, which is good because we were after a vector. Okay, so these, you know, these would be the cross product. Is that okay? And that's the answer. And you can check if you wanted to, which you don't. You can check that this happens to be perpendicular to these two vectors. How? By doing the dot product. So let me just do it once because, like, again, it's not something we had to verify, but it's kind of nice to see that it comes out being perpendicular to the original ones. So what happens if you do u cross v dot u, right? That should be 0 because I told you the cross product is supposed to be perpendicular to the original vectors. So this, like, you can call it like a sanity check. If you like, I mean, in the sense like you don't have to do this, but it's kind of nice to see it at least once to actually check that it behaves as you wanted it to behave. So this gives you dot product between -1, 7, 5. And U, which is 1, -2, 3. And let's see, so this gives you -1 -14 plus 15, right? Which is 0, right? So they're perpendicular, and the same would work, with the other, but I won't do it here, so I'll just put it like also U cross V times dot V would give you 0 because it is supposed to be perpendicular to both of them, right? So again, in practice, you don't have to do that because by construction, it does come out as perpendicular. But like say, that is like a good way to check whether you made a mistake or not. Because if you made a typo, then yeah, like when you do both dot products, you wouldn't find 0 in both cases. Maybe your one came out being perpendicular, but the other one shouldn't be perpendicular if you made a typo. So like that's like if you want like an alternative way to check if you found the correct cross product, you can just like do the dot products to see if you got 0 in both cases. But okay, questions about this? Okay, so for now, that is what we need to know about cross product. So now you have like two ways to find it. Like one is like the geometric definition with the you know with the right hand rule, and the other one is kind of like this more like algebraic version in terms like of the entries of the vectors. I should also put this one like in a box because that's the main formula. So now our next step is to talk about a little bit about lines. So, but lines kind of describe in terms of vectors, so it's a little bit different to maybe how you have described them before, because eventually, and by eventually I mean next week, so what we want to say is that say if you have like a curve in space, which could be like the trajectory of a particle moving in time, then the position vector will give you a curve, but then the velocity vector will be a vector tangent to the line or tangent to the curve. So that is like in the same way which the derivative is kind of the slope of the tangent line. The version in terms of vectors is that if you have like a particle moving in space, like the velocity vector is tangent to the curve that represents its position. Okay, so that is why we need to talk a little bit about lines. So to do that, let me just give you like something else that we need, which I haven't mentioned before, but it's very easy to describe, and that's called like the relative position vector. Put it like that. So the idea here is that let's say you have 2 points P and Q. Okay. So here P and Q are 2 points. Okay, so there you can define a vector which I'll call PQ. Yes. So this is going to be a vector this is a vector that starts at P and ends at the point Q. So in a sense, what this vector is kind of like telling you like the position of the point Q with respect to the point P. So that's why I'm calling this like a relative position vector. So it's kind of saying like, if you want to go to Q from P, along which vector do you have to move on, right? So you have to move along the vector PQ. This vector is like actually important because, like in applications, because many forces do depend on the relative position between, say, two particles, right? So if you have like a gravitational force, then the force is directed along the line that connects the particles. Same with like the blah blah. I mean, there are many forces which are called central that just depend on kind of like the relative position. So it's like a useful vector to have, but like we almost have it. We know how to find a formula almost like what we have said so far, because remember our vectors are kind of being measured or described from the origin. So let's just call this vector R sub P. So this means like this is like the vector that gives you the position of the point P with respect to the origin. So this is the position of the vector P, sorry, of the point P, position of the point P with respect to the origin. And then there's kind of like the same for Q. So I'll call it R sub Q. Okay, so R sub Q is going to be position of the point Q with respect to the origin. Okay, so far so good.
Wait, in this case, you said that RP is just the vector form of P?
Right, it's kind of like the vector form of P. Yeah.
Okay.
Yeah, so I'm just trying to like kind of like make a little bit more emphasis like in the difference between the point and the vector. But yeah, in practice it's kind of like indistinguishable because of what I have said before.
Yeah.
But in this case it's kind of just it's better to make a small distinction so that like the picture is a bit more clear. But yes, like in terms of how you would write them, it's kind of like basically the same. That's it just like would have been a bit, I could have written this P and Q, but that looks a little bit odd sometimes. So we have now, what's the nice thing here? Like we have three vectors, right? Making up a triangle, right? But there is an interpretation, for the addition of vectors in terms of a triangle, which I have told you before. So there are two vectors here that if you add them, give you the third one. I don't know if anyone can see which two. Yes, although I don't want to use the negative, but it's kind of the same. Yeah.
RP and.
Yeah, right. Which is what you're saying. If you add RP to PQ, that gives you RP to PQ, that gives you RQ. So I just didn't want to put like the negative like from the beginning of the equation. So what I'm trying to say is that RQ is like the sum of these other two sides. RP plus PQ. And the important thing here is that already gives you like a formula for PQ by moving this to the other side. So you can like the formula for the relative position vector is just like the difference in the positions of the other 2 points, which makes sense if you think about it, Okay, so the position, like the vector goes from P to Q is just the position of Q minus the position of P. Okay. Is that making sense? So why, I'll do an example about finding this vector in a second. I'm gonna give you first like the equation of the line because it makes more sense to see that as an a direct application. So why is this a useful thing? So let's just go back to lines. So let me just give you a quick reminder about lines on the plane. Okay, so that you see where this becomes useful. So just a reminder. View of lines on the plane. So hopefully you recall that if you had, if you have 2 points on a line, or better say, there's a better way to say this, maybe. If you know 2 points, right? If you know 2 points, there's a unique line that passes through those points, right? That's maybe a better way to put it. Another way to say it is that if you know 2 points, you can find the equation of the line, right? So what was the equation of the line? The equation of the line, there are different ways to write it, but it's like mx plus b, for example. That's one way to think about it. The important thing is that with 2 points, again, I'm mostly focused on interested for now in the direction of the line. So with 2 points, you can find the slope, right? Because the slope is just y2 minus y1, x2 minus x1. Okay. So the point that I'm trying to make here is that 2 points determine a line on the plane. So 2 points. Okay. And so what I'm trying to say now is that essentially the same happens for lines in space. So if you have a line in space, let's see. It's easier to draw first the line and then just choose the points on the line, like in terms of purposes, like for the picture. Let's say I had like a line in space. Okay. I'll put this so just imagine that I get started first by drawing P and Q. So like you draw first P and Q and like then you imagine there's like a line passing through them, right? So that's like the same works now in space. The difference is that it is not super convenient to describe that in terms of a single number, which is the slope. Like the analog of the slope for us will be kind of like a vector that gives you the direction of the line. So there's going to be a vector. So the analog of the slope here of the slope is just going to be a vector that gives you the direction of the line. There's a vector. I'll call it V. For that will make more sense later. You see the direction of the line. Okay, and so for example, what, in fact, let me make this point Q move a little bit closer to P. So I'll put it here. So what is a vector that points along the direction of the line? This one that I'm drawing for you. Okay, so once you have 2 points, you can find the vector that gives you the direction of the line just by using this relative position vector. So this is the vector Q. So for example, you can take PQ, the direction vector to be PQ. Works good. So, and now why is that useful? I'm saying that with that, you can write the equation of the line in a convenient way. So let me explain how I can do that. Because what happens, and I'll give you like a simple interpretation in a moment. So what happens if you have a third point on the line? So what if you have the third point on the line? So let me draw this one here. So now I have 3 points, P, Q, and R. So you have this other, you could have chosen like another vector that gives you the direction of this line. Like, let me try to draw it here. I don't want to, I mean, it should be also being drawn on top of the same line, but then it can get a little bit confusing. So I'll just draw it here, but hopefully it makes sense that this is like what I'm calling PR, right? So this is like the vector PR really should be on top of of this line segment, but it's just a little bit too sorry, PR. So it's a little bit too inconvenient, too annoying to write it that way. So, okay, so if you have a third point on the line, you have these 2 directions, the yellow one and the orange one, but there should be there is like hopefully like you would expect some relation between those 2 vectors. So what can you say about those 2 vectors? They're parallel. Another way to think about it, yeah, they're parallel. So what means that one vector has to be a multiple of the other vector. One is like a rescaling of the other one. So for example, this vector could be 2 times this vector or a third minus 2 times, like depending on where you choose the third point, like you can just rescale this vector and get to the other one. So which is like another way of saying that the vectors are parallel. So what's happening is that they are parallel. They must be parallel. So that means that a vector, so one way to say that is in terms of the cross product, right? Because the cross product then should be 0. That's not too, the 0 vector, that's not too convenient for these purposes. What you want to say is that this vector PR should be just a rescaling of the vector PQ. So it should be the vector PQ times some number, okay? Which I'm going to call T for a reason that I'll explain in a second. So T is like a rescaling factor. It's just like, so it's just a scalar, just a number. Okay. So, but what was this? This was the position of R minus the position of P. Okay, so this is the position of R minus the position of P. If you remember like the formula for this vector, so this is just P times PQ. So what is this? If you kind of like solve for the position of R, that tells you that the position of R is the position of the point P. Let me use a different color now. Yeah, plus T times this vector. I'll rewrite this in a moment, like in a different way, but like what I'm trying to say is that the way to think about this formula is that the way to think about this formula is that this is kind of like some sort of initial position on the line. And then T times this vector is kind of like time times velocity. So essentially the idea is like that, when T equals 0, let me just say it in a different way. So when T equals 0, right? When T equals 0, what's happening? That it's saying that the position at P coincides with the position on R. So T equals 0, you're here, right? And the point of this formula is that then you start moving in the direction of the vector PQ. And so after a certain amount of time, T, you are at this position on the line. So it's kind of like telling you like the formula, the position at time T is like initial position plus like a displacement vector. And on a line, you can move a constant velocity, and so that's why the displacement is just time times velocity. So this is kind of like the position at time t. At time t, in a sense, this is the initial position. And this is like, the net, these two things are kind of like, this is kind of like time. And then this thing would be like the net displacement. So let me just write that down a little bit more nicely. Oops, I don't want to erase this picture. So I'll write it more like in the notation that you would typically see, and this is like the notation that I'll be using. I'll be using for lines. But is that making sense, kind of like plausible? So what I'm saying is that in general, so this is like the equation of the line. This is how you need to know this. So what I'm trying to say is that for a equation of the line, so for a line, you will need, there's two ways to think about it. Like you need a point and a direction. So let's think of this point as P naught. I'll call it P sub naught, P naught, okay? Which is kind of like was working as P there. And then I'll call this other one like R of T. Okay, so and I'll show you how this looks on algebra as well. In a minute. Okay, and then we have this vector V, which gives you the direction of the line. So the formula for the equation of the line is that R of T, the position at time T, is the initial position, which I'm calling P naught, plus T times the velocity vector, which is how which is how we'll think about this, or use this more thoroughly next week. So V, let me say where V, for example, where if you know 2 points on the line, if you know 2 points P on the line, 2 points P naught and P1 on the line. And you can take and B to be, you know,
That formula, are you treating P naught as a vector?
oh, so, peanuts, okay, sorry, I should, it is, yeah, in practice, like I will, but let me just, thanks. Good catch. Let me put it like this to make it look better, but yeah, in practice, like you kind of like forget too much, forget a little bit of those subtle distinctions, but yeah, so like this is kind of like our peanut, yes, thank you. So yeah, it's just kind of like saying, how much are, what's your position on time P? You first move in the, to get to P naught, that puts you on the line, and then you move in the direction given by the yellow vector. So that's not one way of to think about that some formula, but yeah, thanks. So let me do an example to make this a little bit more concrete. I'll finish with this example, and then next time I'll tell you about planes, which is the other topic that we need from this section, so. Oh, here's, so this is sometimes also called the vector equation of the line, because you see, like you're using vectors. So let me just call this vector equation of the line to describe this. This is a vector equation of the line. And I'll compare it, I'll rewrite it in a way that's easier to compare with, you know, the version on the plane. But let's say that the P naught is, I'll put it like 1, 1, 2, and find the equation of the line, find the vector equation of the line that passes through this point and this other point. Okay. So let's compare this with what we need. We have the 2 points, so we have an initial point, which I'm calling P naught. The 0 is just for time 0. So just to remind you, that's how you imagine that you're walking on the line with a timer, and you set the timer at 0 to be where you're at P naught. Okay. And then for the line, you only need this vector. In addition to an initial point, you only need the vector v, but the vector v can be taken. So here's the solution. So you just take v to be P naught P, the vector P naught P1. Okay, but that is just a position vector of P1 minus the position vector of P naught. But that's what is that? I mean, that's essentially these two things, but if you prefer, you can write them in terms of ij and k so that it looks a little bit better. So you can write it as 2i plus 3j. That's P1, right? Minus k. You could also have left it in terms like of the common, like this point notation, but just to kind of like think of them more explicitly as vectors. I'll do that. I plus j minus 2k. And so what does that give you? It gives you 2i minus I, that gives you I. And then 3j minus j gives you 2j. And then minus k minus 2k gives you minus 3k. Which is the same, like, numerically what you get if you just subtract the entries, right? So 2 minus 1 is 1, 3 minus 1 is 2, and minus 1 minus 2 is minus 3. So it's like, whether you want to write it, like, I'll put it also like, if you prefer, like, as a point, like. But I just want to kind of, as a listener for this today, kind of like keep a little more of a distinction between the point and the vector. But in practice, like, it's like the entries are essentially what you get by subtracting the entries of the points. So it's not like there's nothing like, too fancy about that. So that is the direction of the line. Okay. And we're almost there. So the vector r of t, the position of the vector, the position vector r of t is just p naught, well, or the position of p naught plus p times this vector. So what is the position vector p naught? It's just I plus j plus 2k. Plus c times the vector, so plus c times plus 2j minus 3k. And again, if you want, just practice, like, for computing it, it's just easier to write it in terms of the coordinates, that you also could have done that. Just look at a little bit easier to work everything out. So you can go back and forth, that's fine. And so if you do that, then that just gives you 1, 1, 2. Remember to multiply a number by a vector, you just multiply each entry, so you get t, 2t minus 3t. Okay, so that gives you 1 plus t, 1 plus 2t, and then 2 minus 3t. So this is telling you, like, the position, like the x coordinate as a function of time is 1 plus t, the y coordinate as a function of time is 1 plus 2t, and the z coordinate as a function of time is 2 minus 3t.
I don't think this is like super relevant, but when you plug it in from P naught, if you had a minus 2k, but I think
Oh.
it was just a positive 2.
Sorry, like, let's see. Oh, where,
Like P naught is one positive 2. Plus
he-
is
oh, so,
plus I plus j minus 2k. So this is
oh, you're saying that here, put like a minus 2k when it, no, it does, thanks, like, it
like,
does,
it doesn't matter that much.
right, no, but it should still. Oh, because did I do the subtraction the correct way?
Yeah.
Okay, so but it's still better to have it correct, like everywhere, but thanks. So mentally I did it correctly, but yeah, like, if you had done it with minus 2k, then it does, would have given you something else, but no, thanks. So there. Pretty good. So what I'm trying to say is that these, like, so this is what you would call the vector equation of the line, and then if you think about it, like, a better way to describe this, and I'm almost done, is that, okay, so this is the position of a point on the line. So what this is telling you is like a formula for, the x coordinate, the y coordinate, and the z coordinate as functions of t, So there's maybe it's something that I haven't emphasized too much, but, like, when you have an equality between vectors, that actually is an equality between their entries, right? So that means that the first entry must match the first entry. So that means that x of t has to be 1 plus t. And then the second entry must match the second entry. And so that means that y of t is 1 plus 2t. And then the last one is that the third coordinate matches the third coordinate. So you get C of t. Is 2 minus 3t. So if you write it this way, that, I mean, it is the same as the equation that we have there, but like, since it's kind of like for each coordinate separately, this is called the parametric equation of the line, or the parametric equations of the line. So just to show you quickly how this looks, I mean, it's kind of nice to see how this looks like. And I'll be done with that after I just show you this. So again, you can go to GeoGebra, and so you can enter the points, like I'll call them P and Q here. So it's 1, 1, 2, right? And the other one was, what was the other one? 2, 3, -1, okay. Okay, so those are the 2 points in space. Like, let me show, hide the plane to make it easier. Right, so we're after the line that goes through these 2 points. And again, the idea here is that you can enter GeoGebra, like the command for a line or a curve more generally. So you enter in GeoGebra curve. Okay, so I'm going to give you like, and so I'll explain to you in a second this works. So the first the spot is for the slot is for the first expression of t, which of x, which was 1 plus t. If you look at it, if you review it there, so it's 1 plus t, and then was it 1 plus 2t? And then what is the last one? 2 minus 3t. Perfect. Okay. Cool. So that is like the function that you get to GeoGebra, and then you enter parameter variable name. So the name of the parameter is this variable that appears here. So you're just going to tell GeoGebra that is like from, like, it's going to be called t, and then you give the start value and the end value, because like, you cannot really do it from minus infinity to infinity in practice. So it's kind of like time. So you want time maybe to go from minus 10 hours ago, so like 10 hours into the past, and then 15 hours into the future or whatever. So let's just do minus 10, 15, and there there you get the equation of the line, which is kind of fun. So what will happen is, what then you can ask is, oh, what if you have put other expressions? It's like, not linear expressions in terms of t, but more like t squared or t cubed, things like that. Then you get more random curves in space, right? And that's what we'll start, discussing next time. So, but the most simplest one are lines where everything kind of depends linearly. It's kind of like synonym. Everything depends linearly with the parameter, because everything, like every power of t is like raised to the 1. But just to make a quick modification, if you had put something like, 1 plus t squared, right? So I'm just to change this one here. And then you see, I just curved it a little bit, right? And that means that there's going to be acceleration in the line. If you thought about this as a piece of a roller coaster or a piece of a curve segment, then that means that if a particle is moving this way, there's no way to move along this curve without like accelerating at some point. But on the line, you can always move like without acceleration, which is why the t can be linear. Okay, so it's kind of fun to just play around with the expression, see what you get. If you put like a sign of t, then there should be something that repeats itself, etc. So next time we'll talk about planes, and and next week we'll actually return to this with more time, and I can dig this deeper. Okay, so let me just, because someone needed to copy more board.